Welcome back, grades 7 and 8. In today's video on light and optics, we're going to take a look at what's called the wave model of light. It's our way of understanding how light works and how light travels as a wave. We've we've seen many situations in which light travels in a straight line. It's the best way that we understand how reflection and refraction work. For example, light that shines through a rectangular window will produce a sharp, bright rectangle of light inside the room. Sir Isaac Newton actually tried to explain why this happened. He proposed that light beams are actually made of streams of extremely tiny, fast moving particles. These tiny particles of light, he suggested, could only travel in straight lines. Newton believed that the particles could not travel around objects. And this is why we say that light often travels as a particle. But strangely enough, it's not the only way for us to understand how light works. Light does not seem to consist all the time of tiny particles that travel in straight lines. When light passes through a small opening, for example, it spreads out around each side of the opening. To explain this behavior, the Dutch scientist Christian Huygens, around the 1600s, proposed that light might actually travel as a wave, not as a stream of particles. To visualize this feature of waves, we're going to take a look at the picture that's here. The high part of a water wave is called a crest. The lower parts of between the crests we call the trough. So where we have the peak here of the wave, that's the highest point, we call that the crest. In between that, the lowest points are called the trough. As the wave moves to the right, the duck, that's right here, rises up as the crest passes and then drops down as the trough passes. Just think about being on a boat in a wavy ocean or in a wavy lake. The duck and the water around it do not move forward. They just move up and down as the wave passes. The distance from crest to crest, or from trough to trough, we call the wavelength. We can also think of a wavelength as the distance covered by one complete crest plus one complete trough. So here, there's different ways we can think about how long one of these waves is, but we can think about either a wavelength being from the top of one crest to the top of another crest, or from the bottom of a trough to the bottom of a trough. They're going to be the same thing. Wavelengths is something that we're going to explore a little bit right now, but it is something that as we take a look at how waves work and how waves function, they are going to become a major part of your focus in math as well as in physics when you get later on into later in high school and even when you get beyond into college or university. If the wind starts to blow, the water will become rougher. Soon, higher crests and troughs will form. The height of the crest or the depth of the trough from the resting position we then call the amplitude. So the resting position is, let's say there was absolutely no wind. There was no waves. That's the position at which the entire thing is level. Nothing's going up and nothing's going down. The distance from that resting position to either the highest point on the crest or the lowest point on the trough, we call the amplitude. The amplitude is, in this example and in others, a good indication of the amount of energy transmitted by the wave. The more the amplitude, the more energy is being transmitted. The more the amplitude, the bigger the waves are going to be on the ocean or on the lake. The rate at which the duck and water move up and down is then called the frequency. So that's kind of like how close together are the waves. Frequency is the number of cycles completed by a vibrating object in a unit of time. Frequency is usually measured in something that we call hertz, or in cycles per second. So we can think about that as in if something vibrates 20 times in a second, its frequency is said to be 20 hertz. So how does this fit with our wave model of light? Scientists have developed a model of light by looking at how light behaves and then trying to explain what they see. As we've learned in earlier times in science, a model is a way of representing something in order to try to understand it better and to make predictions. Many of us did a similar sort of thing when it came to our science fair projects. One explanation of light behavior is the wave model of light, which pictures light traveling as a wave. This model does not explain everything about how light behaves, but it does help explain a great deal. Thinking about light in terms of waves helps explain otherwise unpredictable behavior, such as why light can curve around an opening. Just as for water waves, the distance between the crest or the trough of a wave of light as it travels through a space is called a wavelength. When light passes through a small opening, the waves spread out. How far the waves spread out depends on the wavelength of the waves. Waves with shorter wavelengths spread out very little. Waves with long wavelengths spread out more. And we're going to see different ways in which that is used in action in the world around us. One of the ways that we can understand a little bit more about light waves, and one of the ways in which we see it in a remarkable way, is in sunsets. We can explain sunsets, like the one that we see here, using the wave model of light. As light waves from the sun travel through Earth's atmosphere, they strike particles of different sizes, including dust and grit. The longer wavelengths of reds and oranges tend to pass around these particles, whereas the shorter wavelengths, especially blue and violet, strike the particles and reflect and scatter off them, as we see in this image here. At sunset, the sunlight we see passes through about 700 kilometers of Earth's atmosphere. At this time of the day, the sunlight passes through many more particles than earlier in the day. And so this allows plenty of opportunity for many of the blue and violet waves to be reflected away. Red and orange waves remain to color the clouds of the sunset. Some of the waves with shorter wavelengths are reflected into space. However, if you look straight overhead at sunset, you'll see the blue light that has been reflected towards us. There are also different ways in which we can understand the wave model of light. So in 1966, Theodore H. Maiman, a physician at Hughes Aircraft Company in California, became the first person to use a process called light amplification by the stimulated emission of radiation. And if you haven't been piecing those letters together, that is an acronym for what's called laser light. Many of you might not have even known that laser is actually stands for something, and it stands for light amplification by the stimulated emission of radiation. Laser light is quite different from the other types of light that we've been learning about. However, an understanding of the wave model of light helped scientists develop laser light and its different applications. As we've already talked about, an incandescent light bulb gives off many different colors. In terms of the wave model, this means that many different frequencies and wavelengths are produced, as we see here. Moreover, the waves are all jumbled. Crest from one wave might overlap a trough from another, and this makes the waves work against each other, and we call that kind of light incoherent light. A laser, on the other hand, emits waves with only one frequency or wavelength, as we see here. In addition, all the wave line up to work together. Such light is called coherent light. And we use this not only in terms of light, but we also use this in terms of sound. And so we're not going to talk too much about it here, but sound works in a similar sort of way, where it works using wavelengths. And when we're talking about some of these wavelengths, if we have another sound that's coming along that has the same sort of wavelength, we can amplify that sound and make it louder. But on the other hand, if we have another wave that comes around and the wave of one sound perfectly matches the trough of the other sound, they actually end up canceling each other out in a process called noise cancellation. And by the way, this is the way that active noise cancellation works in some of your headphones, is that it actually creates its own wavelength that is exact opposite to what it's having come in, thereby canceling it out, which is kind of a really, really neat way of doing things. But back to lasers. Lasers are used for many purposes. Grocery stores and other retail outlets use laser scanners to read barcodes on products. Um, Over fractions of a centimeter, lasers read digitalized data on our hard drives. A tiny laser beam focuses on a spinning disk surface if you're reading a disk in a computer or maybe even in one of your gaming systems. The resulting pattern of reflections carries that information. You might even see police officers using laser to measure the speed of a car. Lasers can also help us understand a little bit more about how fiber optics work. And we're not going to spend a lot of time on fiber optics, although fiber optics are fascinating, and maybe even some of you have fiber optic internet, which uses light instead of electricity in order to transfer data very, very quickly. Laser lights can be released in pulses or in a continuous beam. In either form, it can be powerful enough to make precise cuts through metal. Laser beams often serve as scalpels in different major surgeries nowadays as well, and their heat can be so intense that it can instantly seal broken blood vessels as neatly as they cut through them. Eye surgeons might use lasers. For example, lasers can shave off areas of the cornea in order to correct problems caused by irregularity in the eyeball shape, thereby changing the refraction through our lens. Surgeons can also focus narrow, intense laser beams onto the back of the eye to spot weld a detached retina. So there's crazy things that doctors and scientists can use lasers for in order to be able to, really do all sorts of amazing things in the world around us. It's also interesting to think about where this could eventually go. For example, one day dentists might be able to use silent laser drills to work on teeth without having to put in anything like freezing or without having to use the normal drills that they use now. And they're also exploring different ways to use laser light to vaporize cavities instead of having to drill into them. And what a wonderful world that might be. In our next video, we're going to again explore more about light, this time going beyond visible light and understanding more about the entire electromagnetic spectrum.